Thanks to LastPass for sponsoring a portion of the video. This is the world's first 1,000 horsepower 2020 Supra, and it's still using the stock engine. Why is that so surprising? Well, when this car came out, people thought the engine was absolute trash. So why is this one with relatively limited modifications able to make 1,000 horsepower? Well, it comes down to this man, Stephan Papadakis, and his mad scientist level of ingenuity. In today's episode, we're gonna go into how Stephan disassembled this engine and rebuilt it from the ground up. We're gonna look at how he used forged parts and why the process of forging is so important. We'll see the reason why so many stock parts were actually worth keeping and how they stood up to that amount of horsepower. And finally, my favorite, we're gonna look at how he used lasers and 3D printed metal parts to push this engine over the edge. You can 3D print metal. I didn't know that, and that's super cool. So get ready. Oh boy. Why would I do that? I gotta say, is that a Supra? Thanks to LastPass for sponsoring this portion of the video. If you're as obsessed with JDM cars as me, you're probably on a million different forums and websites. And all those passwords and usernames get so confusing. But I use LastPass so I can keep all of those in one place. Now, LastPass remembers and autofills your passwords on websites and in apps on Android and iOS. They make it super convenient to just bop around and not have to worry about, oh, is this the password for where I put a number on the end or where I put an exclamation point? None of that. LastPass has unlimited password storage, free cross-device sync, and password sharing, which comes in handy when my homeboys want to hop on the 5G train. Click the link and start using LastPass today. Thanks to LastPass for sponsoring that part of my video. Now, we've seen new Supras before that swap in a more powerful engine, like a 2JZ, to get higher horsepower, but not this one. So why did Stephan Papadakis keep the German-born engine that comes in the Supra? Well, it's because he loves a good engineering challenge. Now, if you don't know who Papadakis is, this guy is an absolute legend. In the 90s, at only 21 years old, he built the first tube chassis front-wheel drive drag car in the United States. The dude has put a NASCAR motor in a Scion. He's built some wild-ass cars with some impressive engines. And now, he wanted to get 1,000 horsepower out of the hated stock Supra engine, the B58. So, where do you start? Well, first, he needed to know what it was really capable of. So he did what any sensible, efficient race team owner / car builder would do. He took a brand new 2020 Supra with 500 miles on it, and he took it apart, disassembling it down to the bare block. And by taking it apart, he could inspect each critical component to determine its high horsepower worthiness, kind of like a crime scene investigator for engine. He could use his skills to, one, figure out how to get more horsepower out of the B58 power plant, and two, would any of the stock components be capable of handling 1,000 horsepower? Also, as a side note, he was the first person to document doing this thing. I mean, this engine was so new that he had to call in favors to his friends overseas to get certain tools to take it apart. And not only that, he didn't have some shop manual or YouTube to help him out. This was a massive challenge. This dude is straight up Oregon trailing his way through the B58 engine. Anyways, when your goal is to get 1,000 horsepower, how do you get there? All right, so first, let's talk about how you get more power just overall in general. And we can start off with our most favorite of equations, the donut equation, which is more air plus more fuel equals more power. And we're gonna focus on the more air variable. Now, the amount of air getting into your engine is the rate limiting factor in our famed donut equation. You can sit there and you can argue with me and you can say, hey Jeremiah, fuel is also a limiting factor, but I tell you, you're gonna run out of air before you run out of the ability to dump more fuel in there, and then you're gonna lose the conversation and look like a nerd. So don't do it. So there are a few ways we can get more air into the motor. One way is to increase the displacement, meaning we can increase the volume of our cylinder. So we can do that by boring the cylinders, which is making them wider, like that, or we can do it by stroking the engine by changing out the crankshaft, and that makes the cylinder taller, like that. That allows the piston to travel down the cylinder further and therefore increasing the volume of air it pulls in. Now Papadakis, he didn't go this route, and he didn't for a few good reasons. Now from the factory, the all aluminum B58 cylinder walls are coated with an electric arc wire spray. And that process starts out with a conductive metal wire that they then heat up until its melting point. And then they take that melted wire and they spray it on the cylinder walls using high pressure. And once it's sprayed on, it forms a very thin layer of iron material about 0.3 millimeters thick. And this layer is extremely wear resistant. It transfers heat really good and it reduces the amount of friction on the piston rings. Now, if you were to go and bore that cylinder, you'd essentially be removing that layer, and that's not good. So what about stroking the motor? Well, when Papadakis dismantled the engine, he took a good CSI look at the crankshaft, and it was a beefy one. Not only was it beefy, it was forged. And I'm gonna get into forged parts and explain why that's important in a second. But for now, let's just know that there wasn't a need to swap out the crank just yet. So if he didn't bore it or stroke it to get more air into the cylinders, what did he do? Well, another way we can add more air is by using forced induction systems. We can supercharge it or we can turbocharge it, hashtag boost creeps. Now both of these methods force more air into the cylinders, and the B58 already comes turbocharged, so that's great. But the stock turbocharger can't deliver the amount of air mass needed to make 1,000 horsepower. You need a bigger turbo to force more air in. So Papadakis went with the biggest turbo BorgWarner makes, capable of flowing 110 pounds of air a minute when it's spinning at its max RPM of 117,000 RPM. Now to give you an idea of how much air that is, say we had a room that's 10 foot wide by 10 foot tall by 10 foot long. It could suck all 1,000 cubic feet out of that room in 41 seconds. That's a lot of air. But slapping a bigger turbo on the B58 creates a bunch more stress on the internal components of that engine. And when we say internals, we're talking about pistons, rods, the crank, the camshafts, the bearings, anything that has a force applied to it during the combustion cycle. Now, if we add in more air and we add in more fuel, we create a much bigger boom, explosion inside the combustion chamber, the cylinders, right? And that bigger combustion pushes the piston down with a bunch more force. And if we're going from 335 horsepower, which the stock engine has, to 1,000 horsepower, almost 3 times as much, we can assume the forces acting on those internal components is also 3 times as much. So, how do you make sure those internals can hold up to all that added horsepower? Well, you make them out of a stronger material. And here is where we'll talk about forged internals. Now there are a lot of ways you can go about making metal parts, but today I'm gonna focus on casting parts and forging parts. So first, let's talk about the most common way of making parts, and that is casting. So casting is a process in which you take a metal and then you heat it up until it turns into a liquid. You then pour that liquid metal into a mold that's in the shape of your part. You then let that metal cool inside the mold where it solidifies, turns from a liquid to solid, and now you have your part. So there are 3 main ways of casting parts. There's sand casting, which uses a mold from sand. There's investment casting, which uses a plaster mold. And there's die casting, which uses high pressure to form your part in between metal dies. And the main principle throughout all those methods is really the same. You heat up a metal, you pour it in a mold, and you let it cool. And by the way, humans have been casting parts for thousands of years. One of the oldest surviving cast parts is a copper frog from 3200 BC, all the way from Mesopotamia. Now we still cast a lot of parts today, not only in the automotive world, but in things like your cooking pans. We got tools. Actually, let me grab a tool. These are pipe wrenches that are cast. and they're really cheaply made. They even say China stamped on it, and they're a piece of shit. I've broken like 5 of these. There is a ton of stuff made using the casting process, and there's a few reasons why. You can cast extremely large parts or parts with complicated shapes. You use casting when you need a part made out of a specific alloy. You can take your molten metals and you can mix them together to achieve the specific ratio of metal you need in your final part. And when you're trying to cut down on costs, once you have the mold made, you can essentially duplicate your part much quicker. Casting is a great way to pump out a lot of identical parts. Cool. That's casting. So what is forging? Well, instead of heating metal until it melts, like in casting, you start off with a solid piece of metal and you shape it using pressure. And that pressure comes from a hammer, old school style, or a pneumatic power hammer or a die, which we typically use nowadays. And even like casting, there are a bunch of different ways you can forge parts. And the reason it's called forging is because when you heat the metal up, you use a forge to do so. In the most simplistic of terms, a forge is just a really hot oven. Now you might have seen on TV swords being made. They're made using the forging process. A blacksmith, he'll be like hammering down on the sword, putting it in the forge till it gets hot, pulling it back out, hammering it again and reshaping the blade. Blacksmiths are freaking cool, man. Welders and blacksmiths. Tough some b****. So when gearheads say their engine has forged internals, we all nod our head and we're like, yeah, cool, man. Yeah, that must be a good thing. And it is a good thing. But why is the forging process better than the casting process? Well, it comes down to grain structure. We're nerding out today, boys, get ready. Now, if we were to take a piece of iron, for example, and put it under a high-powered microscope, we could see that it has a crystalline structure, meaning those iron atoms have a very highly ordered arrangement. And when metals fail is when those atoms slip against each other. So when you cast a part, for example, the liquid metal has a grain structure that goes in all sorts of different directions. And that is not good because now you have a part with non-uniform strength properties. Also, there's always a possibility when you cast parts that you create internal voids due to gas pockets. You're pouring liquid metal in and air can get trapped in between the metal, and then as it solidifies, you now have a pocket of air in the middle of your part. That means different areas of the part will have different densities, which is bad because now as the part cools, it can warp, weakening the entire part as a whole. So with forged parts, you're not heating up your metal until it liquefies, which means you're not introducing air pockets into your part. The grain, those metal atoms, maintain their crystalline structure throughout the entire part. It's uniform, and that is very good, especially in parts that are experiencing high amounts of stress. Because the grain has a uniform orientation, it has a higher impact strength and more resistance to fatigue. So not only are forged parts stronger, it takes more time to make them, the quality of the starting material is usually better, and therefore it's more expensive to make them. So what does all this have to do with this Supra? Well, when you're adding extra boost from the bigger turbo, there's a few weak links in your engine when you apply that amount of excess force. You're talking about the pistons, the rods, and the head gasket. So if this engine is making 1,000 horsepower, that means each cylinder is making about 166 horsepower. That is a lot of horsepower out of one cylinder. That's more horsepower than the entire engine in a 2020 Corolla. I mean, what the heck? That's also a lot of pressure, not only pushing down on the piston, but pushing back up on the head. There's a bunch of forces trying to rip these parts apart. So they need to be made out of a stronger material. And that's why this 1,000 horsepower Supra used forged internals. Now, the forged pistons were specifically designed for this car, and they have coatings on the top and on the side skirts. And the top coating is put on there to help resist heat on the dome of the piston, and the coating on the skirts help reduce the wear on the cylinder bores. And the rods, they were designed specifically for this motor using 4330 pre-hardened chromoly steel forging. If you're curious what that number means, good, because I'm gonna tell you. Carbon and alloy steels use a standardized 4-digit number to classify the type of steel. And the first 2 digits tell you the main type of material. So 43 tells us that it's a nickel, chromium, molybdenum steel. And the last 2 digits, they tell you the amount of carbon present in the steel in hundredths of a percent by weight. So 30 means it's 0.30% weight carbon. And that's all very good and cool, and you can impress your friends with it. But if you take anything away from this, it's that these are extremely well-made, forged parts. Now, to keep the head on tight, remember, we have a lot more cylinder pressure now from the added boost. They needed special ARP studs, which allowed the head bolts to be torqued down to 135 foot-pounds. That means with a 12-inch ratchet like this, you have to put 135 pounds of pressure to torque those bolts. Average weight of a 12-year-old is probably 135 freaking pounds. Half of y'all watching this can't even lift 135 pounds. Weak ass. I know y'all just at home watching videos, do some push-ups. And that leads me to my next point, and that is the surprising amount of stock internals used in this build. I mean, it uses the stock head gasket, the stock cams, the stock crankshaft, the stock piston rings, even the stock rod and main bearings. The engineers over at Toyota/BMW engineered the factory engine to be able to withstand a lot of horsepower. New age 2JZ, anybody? Maybe. I don't know. I'm kind of saying it. I'm saying it is. I'm saying it's better. Fight me in the comments. Come find me at my house. We'll have a verbal lashing. 2JZ's better. No way, bro. B58's better. Come convince me. Oh, dude, you're so lucky I can't come over there and whoop your ass. Oh, you're lucky I can't come over there and whoop your ass. I'd whoop your ass so hard. So I want to talk about a few of those stock parts, specifically the head gasket, the bearings, and the piston rings, because to be honest, I think it is quite amazing they were able to use those parts. Now first, let's talk about the head gasket. Now the head gasket function is to create a seal in between the engine block and the cylinder head. And then you may have heard of people blowing head gaskets, right? To understand why that happens, we need to talk about compression ratios. Now, compression ratios are actually pretty easy to understand. So you have your cylinder, right? Yep. And there's a certain amount of volume in that cylinder. Well, a compression ratio is basically the volume of that cylinder when the piston is way down here. And then as the piston compresses all that volume of air, there's a little gap at the top. And so it's the ratio of the volume when the piston is down here to when the piston is at the very top. Typically, it's in the range of 7-to-1, 8-to-1, and high horsepower and race motors that are running off race fuel, it's in the 10.5 to 11-to-1 ratio. But at the end of the day, all that you need to know is that that number determines what kind and what type of head gasket you can use. So we use this fancy fun equation. We find out our final compression ratio is 39-to-1. And remember, that's not only the pressure pushing down on the piston, but pushing up on the cylinder head. So you need a head gasket that can keep the seal between the head and the block when that pressure is that high. And in the case of this 2020 Supra, they can use the stock head gasket, which is pretty crazy given that this engine is putting out 40 pounds of boost to make that 1,000 horsepower. Now, there are a bunch of factors that go into blowing a head gasket. A bad tune, meaning your air-fuel mixture is off, too much heat, pre-ignition, etc., etc. So a high compression ratio isn't the only driving factor, but regardless, you need a high quality head gasket, and the stock one is that. The next stock internal on the list are the rod and the main bearings. In an internal combustion engine, the connecting rods, they're attached at one end of the piston, and on the other end, they're attached to the crankshaft. And then your crankshaft itself is attached to the block. So the rod bearings, those are the bearings placed in between the rod and the crankshaft. And the main bearings, those are placed in between the crankshaft and the block. And in the case of this 2020 Supra, those bearings have a special coating. And the reason they have a special coating is because of the start-stop function that comes standard when you buy a Supra. Now, a lot of cars nowadays have this start-stop function. Pull up to a red light and your car shuts off. Well, when this happens, there's no oil being pumped to coat those bearings. Now, this phenomenon happens all the time in cars without this stop-start function, but it's not as big of a deal over the life of the engine because you're not turning it on and off multiple times during your commute to work, for example. But in cars with this feature, it obviously happens a lot more. And those bearings are now experiencing more friction and more wear because they're lacking that oil. So to combat this, these bearings are coated. And the 2020 Supra uses a polymer coated bearing that not only improves the wear resistance, it increases the fatigue strength compared to non-coated bearings. And that is great when you're building a high horsepower motor like the one in this car. Now the last stock component I want to talk about are the rings. And if you look at a piston, there are grooves that the rings are retained in, and it's the rings that are actually in contact with the cylinder wall. Now in a 4-stroke engine, there are 3 types of rings. You have your compression ring, you have your wiper ring, and you have an oil ring. And each of those rings serves a specific function. If we start at the bottom of our piston, closest to the skirt, that is the oil ring. The oil ring is used to remove excess oil from the cylinder wall. Let's get all the oil getting splashed up from underneath the crank. Returning that oil using return holes that are in the bottom groove of the piston. Now above that oil ring is the wiper ring, and its main function is also to remove some excess oil from the cylinder. They're like squeegees. Finally, on top of that is the compression ring, and that keeps the pressure confined in the cylinder. And also, it's the job of all 3 rings to transfer heat from the piston to the cylinder walls. And when you make more horsepower, you're creating more heat, and the ability of these rings to withstand that heat and added compression is really important to keeping a healthy engine. Now, this has been just a very long-winded way of saying the internals on the Supra are really, really good. Not too many engines out there can use the stock crank, cams, head gasket, piston rings, rod and main bearings in their search for 1,000 horsepower. But there's one thing in particular that Papadakis needed to bypass that was stock, and that is the direct injection system. So in our donut equation, we've already talked about air. Now we're gonna talk about fuel. Now in a more conventional fuel injection system, the fuel's sprayed into the intake port or the manifold, and then that fuel is then pulled into the combustion chamber along with the air, passing by the intake valve on its way to the combustion chamber. Now with direct injection, the fuel doesn't go by the intake valves, it goes straight into the cylinder. And the reason we have direct injection is pretty cool, really. It improves combustion efficiency, it increases fuel economy, and it lowers the amount of emissions your car makes. So direct injection is actually really cool, but unfortunately for Papadakis, the aftermarket support for the 2020 Supra direct injectors is not there right now. He needs to be able to dump a bunch more fuel through them and be able to control them, and no one makes a system that can do that. So he had to go with a more traditional setup, using fuel injectors placed in the intake manifold. 6 2000 cc fuel injectors to be exact. And because the Supra uses direct injection, the factory intake manifold doesn't have any ports for those injectors to go in. So a completely new intake manifold needed to be designed and built. And this was maybe the scariest part of the entire build. To get 1,000 horsepower, they needed this manifold to work. If they couldn't get it right, they weren't going to hit their mark of making 1,000 horsepower. So what they did is they laser scanned the original intake manifold. They then took that scan and they put it into CAD software and they designed their own. They then 3D printed that CAD model to test fit it on the actual engine. And then they finally 3D printed the intake manifold using aluminum. That's right, you can 3D print metal, people. We're living in the freaking future. This is so cool. So how do you print metal? Well, you use lasers. It's always lasers, guys. Lasers fix everything. It's a process called selective laser melting, and it's really cool, and fundamentally, it's pretty easy to understand. Now first, you start off with a 3D model, right? And then you take that 3D part and you section it into thousands of 2D layers, thousands of cross sections. And this is an additive process. So it's going to build that part one cross section, one layer at a time. Now inside an SLM machine, you have a chamber that's filled with metal powder. And that metal powder is spread across a base plate in a very thin layer, about 2/1000ths of an inch thick of metal powder. That's about half the size of a human hair. Just think about dust. You're just putting dust on top of a metal plate, all right? But it's metal dust, okay? A laser inside the machine then fuses that thin layer of metal powder sitting on the base plate in the shape of your first two-dimensional layer. Now the build plate drops down and a layer of metal powder is then evenly laid across the top of the first layer. The laser then comes by and it fuses the second layer of powder on top of the first, and the process repeats itself until you have all of those 2D layers, all of those 2D cross sections built up to make a 3D part. Now just the plenum for the intake was made out of 6,991 layers that took over 51 hours to make. And because the intake was so large, it had to be broken up into multiple pieces where it was then welded together to form a single piece. This is by far the coolest part on this car. And what's even cooler is that it worked. I mean, it was a huge engineering challenge and they were able to successfully make it. That's the best part. Whenever you engineer something and it works out great, and that speaks to who Papadakis is and why he did this build in the first place. Hear it from the man himself.
So for me, I love motorsports, but it's not always about the driver and the championship and the cars going around the track and seeing who's winning. I really love to see the vehicles themselves and how they're built, and wish the teams on the highest levels like Formula One and NASCAR and such would share more of how the cars are engineered and built, to really see a lot of that, you know, ingenuity that goes into those, and then potentially even take some of what we can learn from them sharing on their race cars and apply it to the cars that we built.
We want to thank Stephan Papadakis for giving us a bunch of his time to talk about the Supra, as well as John Sybil, who designed the body kit on the Supra and the render we used throughout the video. Thank you so much. It's really great stuff. And we only dove into a fraction of this build. If you haven't already, go to his YouTube page where he goes in depth on not just the engine, but the roll cage, the suspension setup, anything and everything you could imagine. He has some seriously great content on there. All of us at Donut have watched his videos. They're really great. Go support him too. And then, dude, we got Donut every day of the week now. James has got a new show. It's called The D-List. Check it out. That's on Fridays. So click like, subscribe. And we here at Bumper to Bumper, we actually need your help. If you want your car's footage to be featured on this show, follow us on all our social media accounts. We'll be putting messages out there, letting you know which cars we'll be featuring on the show in future episodes. And then you could possibly see your car on an episode of Bumper to Bumper. So follow us, send me a message if you got a car that you want to see on the show that's got a cool engineering aspect to it. Bye for now. I love you, Mom. Woo! Oh boy. Why would I do that? I gotta say, is that a Supra, and then do the thing, right? What an